Hey everyone, welcome to this explainer on dividing polynomials and adding and subtracting rational expressions. If you're the kind of focused learner who loves seeing how the inner gears of math actually turn, well, you are in exactly the right place. We're doing some heavy algebraic lifting today. We're going to conquer two absolutely fundamental concepts: dividing polynomials and combining rational expressions. So, grab your mental hard hats and let's dive right in.
Here is our roadmap for today. First up, we'll divide polynomials. Second, we'll verify that division by multiplication. Third, we'll combine rational expressions. Fourth, we'll learn how to avoid the dreaded denominator trap. Fifth, we'll run through a couple of knowledge checks. And finally, number 6, a quick recap and a transfer task.
Section 1. Divide polynomials.
Okay, so think of polynomial division just like the old-school long division you learned way back in elementary school, but, leveled up with algebraic terms. It's really just a predictable, logical loop. Step 1. You just set up your dividend, a of x, being divided by your divisor, b of x. Simple enough, right? For step 2, you're going to zero in entirely on those leading terms. You divide the leading term of the dividend by the leading term of the divisor, and boom, that gets you the first piece of your quotient. Then, step 3, take that brand new piece of the quotient, multiply it by your entire divisor, and subtract that whole result from your dividend. Now for step 4, we enter the loop. You repeat this exact same process until the degree of your remainder, let's call it Rx, is strictly less than the degree of your divisor. Once you hit that point, you're at step 5, where you write out your beautifully structured final answer, the quotient Q of x plus the remainder Rx written right over the original divisor, B of x.
Section 2. Verify by multiplication. Now, as you probably know, division and multiplication are inverse operations. And what that means for us here is that if we've done our division correctly, we should be able to perfectly reconstruct our original polynomial, the dividend. It's kind of like checking your work in reverse. If you take your divisor, multiply it completely by your quotient, and then add your remainder back in, it literally has to equal your starting dividend, a of x. This isn't just some neat little math trick, by the way. It's a fundamental property of how polynomials work. They form this closed mathematical system where operations behave consistently every single time. So always run a quick mental check or jot it down on your scratch pad using this formula just to absolutely guarantee that your algebraic masonry is rock solid.
Section 3. Combine rational expressions. Moving on to combining rational expressions. This requires some real precision, so here are the 5 vital steps you need to lock in. Step 1, you absolutely must find the least common denominator, or LCD. Algebraically speaking, you just cannot combine fractions of different sizes. It doesn't work. Step 2, rewrite each numerator to reflect those new equivalent fractions. Step 3, once your denominators perfectly match, you can go ahead and combine the like terms across the numerators into one single expression. Step 4 is where we tidy things up. You simplify that final expression by factoring and canceling any common terms if you can. But step 5, well, this is where the true algebra masters stand out. You have to retain domain restrictions. Because we're dealing with variables in the denominator, we have to clearly state which values of x would cause that denominator to equal 0. Remember, dividing by 0 breaks the universe. It's strictly undefined. So those values are completely restricted from the domain, even if they happen to get canceled out during step 4.
Section 4. Avoid the denominator trap.
Okay guys, please, whatever you do, do not fall for this trap. 2/5 plus 1/2 does not equal 3/7. You can't just mash the numerators and denominators straight across. I mean, think about it for a second. 3/7 is actually less than 1/2. How on earth could adding a positive quantity leave you with less than what you started with? No way. The correct method applies to both simple fractions and these complex rational expressions we're working with. You always have to create equivalent fractions using a common denominator. Algebraically, a over b plus c over d equals the quantity a times d plus b times c all over the common denominator b times d. That rule, it's totally non-negotiable. It is the only way to ensure you're actually adding pieces of the exact same size.
Section 5. Knowledge checks.
All right, let's put this into practice. Here is check number 1. If a polynomial p of x is divided by the binomial x minus a, and the remainder turns out to be exactly 0, what does the remainder theorem tell us about that binomial x minus a? Try to think back to the relationship between remainders and the factors of a polynomial. Take a quick mental pause here before we reveal the solution.
And here's the answer. The remainder theorem explicitly states that the remainder of dividing p of x by x minus a is actually equal to p of a.
So if that remainder is 0, it means p of a equals 0. And if p of a is 0, then x minus a divides perfectly into the polynomial without leaving anything behind. Therefore, x minus a is absolutely a factor of the polynomial p of x. If you nailed that one, your understanding of polynomial division is perfectly on track.
Let's try check number 2. When adding the rational expressions a over b plus c over d, what is the correct algebraic sum, assuming neither b nor d is equal to 0? Remember what we just talked about. Don't fall into the trap.
The correct answer is the quantity AD plus BC divided by BD. How do we get there? Well, by finding the common denominator BD, we multiply the first fraction by D over D, getting AD over BD. Then we multiply the second fraction by B over B, getting BC over BD. And since the denominators now finally match, we can safely combine the numerators. Excellent work if you successfully visualize that whole algebraic process in your head.
Section 6. Recap and transfer task.
Here is our quick recap. Polynomial division breaks expressions down into a quotient and a remainder, a process that is completely and entirely verified by multiplication. Adding and subtracting rational expressions requires finding an LCD, combining those numerators, simplifying, and strictly retaining your domain restrictions. You simply cannot add denominators directly. Equivalent fractions must be created first to produce any valid sum.
And now, I'm going to leave you with this transfer task to try on your own. Evaluate and simplify the rational expression 3 over the quantity x plus 2 plus 4 over the quantity x minus 1. Go ahead and find your common denominator, combine them, simplify, and most importantly, do not forget to state those domain restrictions for x. If you can solve this, you have officially mastered today's core concepts. But before we go, ask yourself this. What actually happens when these complex rational equations represent real-world physics, like the invisible flow of electricity or the precise trajectory of a rocket? Mastering these algebraic structures today means you're literally building the keys to unlock those universal laws tomorrow. Keep analyzing, and I'll catch you next time.